I'm a chemist, which means I'm interested in molecules, their structure, their properties, how we make them and how we can manipulate them to do useful things. Now my interest really comes back to when I was a child and I got to play with Lego, because Lego and molecules are a bit the same. They're sort of abstract fixed shapes that can stick together in fixed ways. But you can make very complicated structures if you put them together in a program sort of way and make something that can do a useful function that you've designed. So it's tapping into my inner child, and I'm really getting to play with Lego for the rest of my life. The sort of molecules that really excite me are the sort of molecules that I can excite, and by that I mean I shine light onto these molecules. And when these molecules absorb light, they start doing useful and interesting things. They can emit the light, they can reflect the light, or they can absorb the light. It's putting energy into the molecules and giving them a little zest, if you like, to go and do something. And I want to actually control what they do and how they do it, because it then makes them a very useful chemical tool. The real value of these sorts of molecules that respond when we can put a signal in like a light source is that we can use them to detect other molecules that might be of interest to us. These molecules are often in very complicated environments. It can be a biological cell, it can be an environment like river water, it could be an environment on another planet. From a chemist's point of view, they're very complex molecular environments. There's lots of potential competition and interference. So the trick is to design a molecule that will seek out the molecule in that environment that you're interested in and only emit the signal when it's found its target molecule. And it's a bit like they shake hands at a molecular level, and then the molecule you've made waves and says, "Yoo-hoo, I found it." And that's really very, very useful then further down the line for people who are then interested in looking at these sorts of molecules in those particular environments. Well, a really big area for this kind of chemistry to be applied has been in the biomedical sciences, in particular the detection of diseases. And there's a number of techniques that are available to doctors to try and diagnose and treat diseases. And we're constantly trying to refine them, because really the challenge for the doctor is to try and diagnose a disease as early as possible so they can start teaching the patient. Now, I'm not a medical doctor, and to me the challenge is purely a chemical one. It's the idea of getting a molecule that can respond to a particular trigger into a human body in a particular set of circumstances and emit a signal which will tell a clinician in an easily readable way, because they're not a chemist, that there's a disease going on or there's some kind of process beginning that might mean that they need to intervene. And so we make these molecules which have all sorts of structures on them which allow them to interact with defined structures in the human body. And so I'm working with a company at the moment to design a particular type of molecule which will go into a cell and basically tell you when the cell is feeling a bit stressed. So this is important to the company because A, it's an indication of a disease state, but more importantly, when they're developing new drugs, they need to know whether the drug is going to treat the person and not cause a toxic effect. So they want to know if a drug, when it's going through its preclinical trials, has any kind of toxic side effect. And a good early indicator is if the cell gives off any indication of stress. So I'm designing a molecule which is basically like a flare for the cell. You put it in there, and if it says it's been tested on with a new type of drug, if the cell says, "Oh, I'm feeling a bit stressed now," it can basically fire this flare off, and in such a way that the clinician or the doctor or the company researcher who's doing the testing can see at a glance which cells are feeling stressed and which ones aren't. And it won't require them to have any chemical understanding of why the molecule is doing what it's doing. All they'll need to do is see the fact that this molecule is emitting light. And it should allow them to screen a larger number of potential drugs through a wider array of cells more rapidly. And there's obviously also the potential to automate this, so that you can have a machine which is scanning all the cells and checking the ones which are having the light being emitted and showing some kind of stress. And in that way it allows the researchers to process vast amounts of data. For me, as a chemist, again, I'm interested in the idea of molecules working in complicated environments or harsh environments, and so it's designing them to have the properties to do what they want to do. So in the previous example I was talking about a biomedical application, but I'm using exactly the same chemistry in an environmental application, in particular in the area of road markings. Quite an innocuous looking sort of thing that you might just take for granted as you're driving along, but they're a vital piece of road safety. But if you look at them, and you'll see in some parts of the country, the markings are wearing out. They don't show up in poor weather conditions or at night. And at night in particular, you want them to be able to reflect light. I'm working with a company that's responsible for laying road markings down in the UK. Now they have a mixture of chemicals which they apply to the road, and it achieves a certain performance that they need in terms of durability on the road and showing up visible under car headlights. But they want to make better road markings, smarter road markings, and to do that they need to understand why they have all the various ingredients in there and what additional compounds they can put in to make the road markings perform better. As a chemist, it's a challenging problem because it's quite a cocktail of compounds in that material, and they're held together in a polymer-like mix, so it's a bit like a sort of really thick gooey plastic which they apply, and it's got to stick to the road. You don't want the car to skid when it hits the road marking, and it's got to show up clearly and distinctly. And of course you've also got different types of colours. We're all used to the white road markings, which are very common, but you've got the yellow and various other indicators which will have to broadcast information to the driver that's very accessible to the driver and instantly understandable and interpretable.